హాయ్ ఫ్రెండ్స్, ఈరోజు మనం రీజనరేటివ్లో ఫీడ్ వాటర్ హీటర్ పెట్టినప్పుడు ప్రాబ్లమ్స్ ఎలా ఉంటాయి అనేది ఒకసారి చూద్దాం. ఓకే, ప్రీవియస్ క్లాస్ we discussed regenerative problems. So regenerative feed water heater. ఓకే, దీంట్లో ఇప్పుడు ప్రాబ్లమ్స్ ఎలా ఉంటాయి అనేది మనం ఇప్పుడు చూద్దాం. ఓకే, నౌ ఇన్ హియర్ ప్రాబ్లం, look at this problem here. An ideal regenerative cycle operates with dry saturated steam. డ్రై సాచురేటెడ్ స్టీమ్ దగ్గర మనకి ఇప్పుడు ఈ రీజనరేటివ్ అనేది సైకిల్ అనేది ఆపరేట్ అవుతూ ఉంది. ద మ్యాక్సిమం అండ్ మినిమం ప్రెషర్స్ బీయింగ్ 30 bar and 0.0 bar. The maximum pressure and minimum pressure is given here respectively. The plant is installed with a single mixing type feed water heater. ఒక సింగిల్ మిక్స్డ్ విత్ ఫీడ్ వాటర్ హీటర్ అనేది ఫిక్స్ చేయబడింది. ద బ్లీడ్ స్టీమ్ ప్రెషర్ ఈజ్ 2.5 bar. ఇక్కడ వచ్చేసరికి ఏంటంటే 2.5 bar అనేది మనకి ఈ ప్రెషర్ వచ్చేసరికి ఏంటంటే ఫీడ్ వాటర్ యొక్క ప్రెషర్. ఇక డిటర్మైన్ ద మాస్ ఆఫ్ ది బ్లీడ్ స్టీమ్. అలాగే పాయింట్ బి, ద థర్మల్ ఎఫిషియన్సీ ఆఫ్ ది సైకిల్. సి, ఎస్ఎస్సి ఇన్ కేజీ కిలోవాట్ పర్ అవర్. సో నౌ దిస్ ఈస్ ద ప్రాబ్లమ్ ఈస్ గివెన్. So in this problem, how to solve? Okay, you will see in here solution for this problem. Now here first we go to draw the efficiency diagram for this given problem. Okay, and before going that, the plant is given here, the data. So given, first you can write down here, given the maximum and minimum pressures being 30 bar and 0.04 bar. So now you can take here P1 is equal to 30 bar, P2 is equal to 0.0 bar, and now respectively the plant is installed with a single mixing type feed water heater. The bleed steam pressure is 2.5 bar. Bleed steam is here, you can take this is P3 is equal to 0.04 bar. In feed water యొక్క ఎఫిషియన్సీ డయాగ్రామ్ ఎలా ఉంటుంది అనేది ఇప్పుడు మనం చూద్దాం. ఓకే, now we take here T, we take this S. Now temperature and entropy. The pressure is going first, this is called here 1, this is 2. Okay, and now go for 3 steam. Okay, this is for 4, you can take. Okay, this is actual diagram for Rankine cycle, but here feed water is adding. So now 3 2 4s we take feed water, and going this fifth one, and now this is called 6s. Okay, and now we take this is 7 in here. The adiabatical process is here. We are drawn like this. The adiabatic curve is acting like this. Now this is acting going. We take here P is equal to constant. Here also P is equal to constant. Here also P is equal to constant. Now the pressure is moving in here 30 bar. It is called 1 kg of mass. Now here P2 is equal to 2.5 bar. This is m kg. Now here P3 is equal to 0.04 bar. This is 1 minus m kg. Okay, this is the given data for this. Now we are going to draw enthalpy and entropy diagram here. Enthalpy and entropy diagram. First we take this is Rankine cycle యొక్క enthalpy diagram. Now in Rankine cycle we see here 2 to 3 and 3 to 4. I'm going like this. 4s. This is 3s. Now here the height. This is 7. This is 5. This you can take 6. Here the adiabatic process will touch all the points. Similarly, this is constant, this is constant, and this is constant. And now this is 1 minus m kg. This is m kg. This is 1 kg. Now this is P1, P2, P3. This is the enthalpy diagram for this problem. Okay, now we are going to start the problem. P1 is equal to 30 bar. Already we written here, and now we take from steam tables for P1 30 bar. Okay, in here the values H2 is equal to 2820.3 kilojoules per kg. What's the unknown values we are going to take with the help of steam tables in here? Oh, you know that very well. Why? Because before so many problems we solve like this. these values are taken from stream tables, but in here S2 is equal to S3S, process 2 to 3, okay. Now that is S2 is equal to SF plus X3S plus SFG. You know very well this equation. So now we here substitute the values. Substitute this all values in here. 5.4448. Therefore we get X3 is equal to, now dryness fraction it will come. So therefore H3 is equal to, we know very well, HF plus X3 plus into HFG. We take these values from the stream tables, okay. Thus the values are plus into 2281.0. now that is equal to, it will come 0.68 kilojoules per kg. So in 2 to 3 process, in here 3 is this, okay. No, pressure not here. Come to here 2 to 3, the pressure is acting 2.5 bar. From steam tables, pressure is equal to 2.5 bar. You take these values from 2.5 bar, okay. Also so we complete here 2 to 3. Now we go for 3 to 4. Look at this diagram, 3 to 4. So the 3 to 4 in here, S4 minus, sorry, S3S minus S4, we can write down here. So directly we go, we are not here to come to 2 to 3. Now we take here from this 2 to 4S. Now directly we go for 2 to 4S, okay. Now in 2 to 4S, what happened? S2 minus S4S, you can write down that equation. So now that is S2, we know. Now here S bar, 4S is coming from pressure is equal to 0.04 bar. మీరు గమనించాల్సింది ఏంటంటే ఈ 0.04 బార్ దగ్గర స్టీమ్ టేబుల్స్లో నుంచి నేను ఇప్పుడు వాల్యూస్ కలెక్ట్ చేస్తున్నాను, ఓకే. ఆ వాల్యూస్ ఐ సబ్స్టిట్యూట్ హియర్ డైరెక్ట్లీ. we know that equation here, this is called SF value. Now this is X4, we don't know, into SFG, this is called SFG for pressure 0.04 bar, okay. Therefore X4S is equal to 0.1, approximately it will come this value, the dryness fraction of this. Now we are going to find here H4S. In H4S also same thing, the point pressure is 0.04 bar. So 0.04 bar pressure దగ్గర steam values I can take here these values for HF directly. Now X4S we know very well, into HFG is 2433.1. Now calculate this. kilojoules per kg. So similarly, next we go for here at pressure P not bar. Okay, we take here H5. We are going to pump. Now the turbine will finish here. 2 to 3, 2 to 4 turbine is completed. Now we go for here directly pump. The pump values here 5, S6, 7 and 1S. You can take this 1S. Okay. So H5 is equal to in here 1 to 1.4 kilojoules per kg. So similarly we are write down here V5 is equal to 0.01004 meter cube per kg. Therefore condensate pump work. So now we are going to pump work here H6 minus H5 in enthalpy diagram. Okay, H6 minus H5, you can write down SC here. That is equal to, this value in is equal to, with the help of pump, V5. Why? Because the pump is starting from 0.5. Now we can write down V5 here 2, 3. The pressure is acting here 2, 3. 2, 3. Now you can take here P2 minus P3. This is the value of H6 minus H5. Now write down V5 value in here. P2 value write down and P3 value you can write down. That into, these all are coming from the units conversion here. You can change this unit conversion. So directly the answer it will come around kg. Now this is called H65 minus H5. So yes. So now we can solve. Therefore H6S is equal to 0.247 plus 1 to 1.4, that is equal to 1 to 1.65 kilojoules per kg. At, now we go for pressure. Okay, 2.5 bar. Similarly H1 is equal to H7 plus V7 P1 minus P2 10 to the power of 5 cube. I write down this equation directly in here. Okay, why? Because I need to find here H1. Now we are going to here 7 to 1. Now this is, you can write down here H7 minus H1 minus H7 is equal to V7 P1 minus P2. Pressure P1 P2. Okay, 1S7. Similarly I write down this. Now I can find here H1. Okay, you put S. I take these values from pressure 2.5 bar from steam tables. From steam tables at pressure 2.5 bar. Okay, this is the all values I noted. 30 minus 2.5 10 cube 5. Okay, So we can write directly 10 square also. Now here the calculation of this thing in kilojoules per kg. So now this is called H1S. Okay. Now we are find out all values. Now we are going to find first A point, mass of the plate steam. Look at here, we find a second, third, 4, 5, 6 and 7 1s. So the cycle will completed here. The total values we find out. Now you are going to here mass applying the energy balance of the feed water. Applying energy balancing of the feed water. Okay. So applying the energy balance in feed water. So you can take here M H3 plus 1 minus M H6, that is equal to 1 into H7. Therefore M is equal to H7 minus H6, that divided by H3 minus H6. Okay, now we know the all values here. So substitute this all values. Substitute this all values. .68 onto 1.65. Now we get the answer here, kg for kg of stream. This is the answer for mass. Now next point we are going to find out here thermal efficiency. Thermal efficiency. So thermal efficiency, we know the problem, total work network done divided by heat supplied. So first we going to find out here turbine work. Turbine work WT is equal to H2 minus H3S, and now plus 1 minus M into H3 minus H4S. Taken here 1 minus M. Okay, the value of H2 minus H3S, alage H3S minus H4S, that's it will come here 1 minus M kg. Okay, now substitute this all values in here. Substitute the all values in here now. Two, 4, 5, 2 minus 1862.1. Now the value we will get here 835.67 kilojoules per kg. This is called M. We find here M value. Okay, before here you look at this. This is the M value we find. This M value I substitute in here. Okay. Now we go for pump work. So pump work also you can write here WP is equal to, starting from here pump work is 1 minus M into H6 minus H5. So H6S minus H5 plus 1, the kg of 1, now here 7 to 1. So here we can write a H1S minus H7. Now this equation you can substitute all values. Plus 1 HS1 you can write down here. Now HS7 also you can substitute. Finally, we get the answer for pump work done is kilojoules per kg. So therefore, work net is equal to work turbine minus work pump. We know very well. You can substitute here this value is turbine value and pump value to get here the answer of this kilojoules per kg. So we need to find here heat supplied. Now that is Qs is equal to 1 minus H2 minus H1. Yes. Okay. Now the heat is supplied here. This is heat supplied 1s2. Okay. So now you can substitute the values 2802.3 minus 538.34. So you solve this, you get Q. That's called heat supplied in here. Okay. So therefore, thermal efficiency is equal to net work done by heat supply. Now substitute these values in here. Get answer approximately 36% of thermal efficiency. Now go for specific steam consumption SSC. So now SSC is equal to 3600. We know work net. Now substitute in here the work net value. So we get final answer. It will come from SSC kg per kilowatt hour. Okay, this is the solution for this problem. Tomorrow we will see another problem. Okay, thank you.